morning, guys. I think it's time to get started. So the talk is really all about this whole new, if you may, emerging, in at least in our view, paradigm of NewSQL. So we're going to cover a lot of the concepts and then walk through some demos. So the demos will essentially walk through some design patterns in NewSQL. NewSQL is really a term that has been coined to some extent categorize a new breed of products which stick to SQL as the fundamental interface, but a lot of the characteristics are the same as what you see with NoSQL, which is the ability to provide you very high scale and at a reasonably high performance, right? And a lot of the focus is really around memory orientation and distribution of data, right? So in some sense, compared to NoSQL, it has far fewer compromises in terms of, especially in terms of query processing and transactions. We'll talk about that. So by the way, I'm Jags Ramnarayan. I don't know anymore what I do in VMware. Just do a lot of meetings, I suppose. Evangelize a lot. I'm specifically involved with the GemFire and SQLFire initiatives. I'm also actively participating in a variety of our data strategies going forward. Joined with me is my colleague Guillermo Tantachuco.
That was close.
Boy, our names are so complex. My name is so complex, you know. But I assure you the presentation is a lot simpler, somewhat dumbed down. So I know a lot of you here are already somewhat familiar with SQLFire. So feel free to jump into the questions. If the time doesn't permit, we might push it out. But yeah, I mean, maybe we could keep it somewhat interactive. We have a few demos. They'll generally be walking through fairly basic stuff in SQLFire, so keep that in mind. Before I get going, I always like to take on sort of the relational database, because at the end of the day, we vendors and new solutions are trying to take a little slice of the SQL market. So if you look at the sort of the relational database, how it evolved and emerged, literally 2 decades ago, came out with very good principles of data independence, isolation semantics, integrity semantics, as we all know it, the asset semantics. But in some sense, the design center has really been rooted in the past. It was designed when memory density was not there, memory was scarce, networks were fairly unreliable, packet loss was pretty common, and the designers chose what was right back then, which is to make sure that if you're changing data, writing data, do everything to make sure that safety is first and foremost ensured. And the entire design center was all about I/O optimization. How can I write to disk very efficiently and read from disk very efficiently? And sort of, if you look at this picture here, it kind of depicts, I would say, the common how typical database engines work, right? You have, disk data buffers, you have an I/O system, you have a transactional system, and what you find is when you look at the buffer management, essentially, much like what we do in a new range of products, we all essentially use memory effectively. But in the database, essentially, memory is all about I/O optimization. So they'll end up essentially caching contiguous disk blocks in memory. So even if my application is just looking for a single row, well, guess what? I'll land up essentially caching a 16 kilobyte block set of block buffers or a 32 kilobyte block buffers, even though I might be looking for something that's just 100 bytes in size. So essentially, you'll end up wasting a lot of memory just so that I/O optimization is done. The second key aspect of sort of databases is that given the strict adherence to asset properties, they'll end up essentially locking quite a bit, right? And there's quite a bit of research done by Marty and Brown on this thing where, and it's pretty common knowledge, right? Typically, when you land up essentially changing rows in a database, you land up essentially locking your rows. And if there is tremendous amount of concurrency going on, the row level lock essentially escalates to be page level lock. You have more concurrency going on, the page level lock essentially escalates to table level lock, and all of a sudden everybody is throttling. Now, the net effect of all this, I mean, I'm just going to skip, essentially there's a lot of stuff going on in a database where writes are getting buffered. You typically write to a log file, then you essentially turn around and the log files are asynchronously written out back to large B trees, resulting in a lot of disk seeks, that sort of thing. Now, the net effect of all this is that their consistency in terms of response times degrades pretty rapidly, right? And there are a number of factors that play into this thing. If you look at a traditional database, given the nature of SQL, you have a cost-based optimizer. The plan generated by the cost-based optimizer can vary over time. The amount of data that essentially queries depend on can vary over time. The indexes also play a role. Then the more important thing here is the other factors. What happens concurrently? What's going on concurrently in terms of updates and queries have a dramatic impact on what my current query response time looks like, right? So if you look at this sort of chart here, the chart on the left, it's essentially depicting the x-axis essentially showing resource utilization in terms of, and simply a metric that's a combination of CPU cycles, memory being used, and the disk I/O going on. And the y-axis is essentially showing the number of queries. This is essentially representative of a typical OLTP system. And what you really see here is, as one would expect, most of the queries, about let's say 80% of the queries, are in fact consuming maybe 500 resources. I mean, the resource is really a metric, so keep that in mind. But you do see a number of queries, maybe 20%, have a very wide distribution, right? And right up to resources consumption, which is in the 50,000 range. So the interesting thing here is that there's a wide distribution, and we would sort of say, hey, what if most of my concurrent queries are consuming the same amount of resources? So that's kind of what you see in the right here. It's all the queries concurrently being executed, the number of resources utilized is less than 50. Well, in theory, you should expect saying, hey, shouldn't I get consistent response times, right? But what you really see is that there is, again, a wide distribution in terms of the latencies for the queries itself, even though the resources consumed are in some sense limited. And again, there are a number of factors here, right? Right up to what else is going on in the system. And given the fact that I have disk going on, disk I/O going on in the real-time path, things start to sort of pile up one behind the other, again giving you inconsistent response. The point I'm making in all this is that, to me, scaling is just one dimension, and everybody keeps talking about scalability as these new solutions as a way to solve scaling problems. To me, it's about predictability. How can I, irrespective of the concurrent load, give you a design that gives you relatively consistent response times and a consistent behavior also in terms of availability? That's a key sort of design goal, design principle through which we ran through this whole project, if you may, right? So again, the point here is, a highly selective query could be using an index at one moment, getting a huge cache hit rate, and out comes a concurrent query that's doing a massive scan that wipes out all my buffers, and all of a sudden, guess what? It's landing up going to do multiple IOs back to the index, back out to the buffers, that sort of thing. Again, the consistency is lost. And the way we kind of solve it, much like a whole slew of products, it's like, what are they saying? It's raining databases in the cloud, right? So the idea is to really scatter the load, right? Let's actually have a whole bunch of nodes, machines, which now, using commodity hardware, I can sort of suck in that load, and just in time I can sort of elastically grow my cluster, right? So here are the common themes, if you may, in the next generation databases. I mean, this is common in my view across all these paradigms, right? I mean, the NoSQL paradigm with Cassandra, HBases. I mean, how many here are familiar with NoSQL? Actually, a good percentage of the room. And how about data grids like Oracle Coherence, GemFire, that sort of thing? Yeah, okay. Right, so I'll just rush through this, and of course Hadoop also, the Hadoop momentum is also bringing a lot of these things to the forefront, which is that the first thing I see is it's all about commodity shared nothing clusters, right? Everybody wants to sort of say, hey, I don't want to sort of vertically scale, I want to horizontally scale by simply having heterogeneous, for that matter, machines that I can add to my cluster. And I have reasonable network connectivity, and it should all work. The focus is shifting in some sense from I/O optimization on disk to really optimizing on the network. How do I move my payloads, my writes, my reads across a network very, very reliably, efficiently? And it's sort of, that is a level of, there's a lot of thinking around that rather than just thinking about, the traditional disk I/O optimization. Including the data structures, how you manage your data structures also essentially shifting. So that's what it is. It's about distributing data and clustering. That's one paradigm. The other thing is obviously how do you partition? How do you scale? Scaling is all about partitioning a data. How can I spread my data? What kind of partitioning models can I have? What kind of partitioning policies can I have? Is also becoming, obviously very, very relevant. Everybody does that. A lot of the NewSQL solutions are all about key-based partitioning. We'll touch on that. There are obviously trade-offs when you start thinking about just a hash, simplistic key-based partitioning. And then there is quite a bit of innovation going on in terms of how do you move behavior to the data nodes. In fact, what we see is this paradigm shift where no offense to any DBAs in the room, but it's really the developer is in control, and we see that shifting, right, where apps are being built in weeks rather than months and years, where it's the developers in charge. I mean, the developer is not only designing the application, he's responsible for the schema, he's also responsible for the efficiency of the database itself. Sure, once it becomes operational, there are other DBAs involved from an operation, but it is a DBA. So what that also means is, what kind of programming models do you offer inside the database? How do I write my stored procedures? Can it be Java? Can it simply be a Spring application? It's very fundamental, very, very fundamental to how we think, including to an extent which says, can I literally take my database and embed it inside my application server cluster itself and run it as if it's just one thing? So those kinds of topologies for us is very, very important. And of course, HA is the norm. I mean, without a question, you got to at least maintain a few synchronous copies inside your cluster. HA is the norm. In fact, we are saying that HA within a cluster is not sufficient. You really need HA across racks. So they have synchronous copies of data across racks, including now HA, if you look at the cloud-like phenomenon with Amazon and those kinds of guys. I mean, it's rather important that I maintain synchronous copies or near real-time copies of data across my wide area network, across multiple data centers. So availability is not just about high availability, it's about continuous availability. It's absolutely always available no matter what. And that's where you see a lot of innovation from folks like Cassandra, things like that, where it's about eventual consistency. People can live and tolerate essentially loss of consistency for a moment of time, but availability becomes more important. And the last thing is really the ability to add capacity dynamically on demand. This is where it's still a growing area. It's still emerging in terms of how well can I sense what the load looks like at any given point in time? Can I predict what the load characteristics will be in the near future? And based on that, can I essentially expand my capacity? I mean, we see a lot of interest in this area, but in practice, there are a lot of challenges because what we find in real life in a lot of workloads is if you think you can predict the future, it could probably be wrong, right? It's like the Wall Street phenomenon, right? Where you predict and you expand. And when you expand a cluster, if you think about an application server cluster and expand, well, it's relatively stateless. Expanding things are really a matter of, can I start up my processes? Can I get my metadata initialized? And boom, you're done. But unlike here, when you have a terabyte of data and you add additional capacity, it's an extremely outrageously expensive operation to really figure out how do I move large chunks of data. I'm going to clog my network to some extent. I've got to maintain consistency at the same time. And yet I got to make sure that there are no right-level bottlenecks. I cannot lock and create bottlenecks. So it's a very expensive. And then if you're wrong, guess what? You've done all this work for nothing, right? So it's a sort of very tricky problem. All right. And the common way, obviously, everybody's addressing it is through sharding, right? I mean, everybody knows sharding here. So the ability to say the application developer or the DBA decides to say, in what way should I partition my database so that I can take n databases and make them appear as if it's just one, and you're deciding on the dimension in which you want to partition, right? Either it's my customer ID or I use a date-like range to essentially do partitioning. But of course, there are lots of challenges, right? The first thing is, how do I land up doing querying when the query essentially has to cross a few partitions, right? Then you have to hand code that query. You'll land up essentially running part of the query on a subset of nodes, grabbing a set back, and then taking that set and redistributing that set to the other partitions, or all the partitions for that matter, and you would essentially land up doing what a database engine would do really efficiently, which is a nested loop sort of thing, right? Outrageously expensive really because you're landing up moving large chunks of the data over the network and you pay a huge price. And of course, let alone, if you want to do any sort of aggregations, ordering, grouping, things like that, it becomes really, really difficult. And the other problem is if at all you land up changing your partitioning dimension, if at all you land up changing how you want to partition your data, well, guess what? You probably have to rewrite your entire application, or at least that portion of the application that deals with data. Very expensive to sort of do. And then the other part is really transactions. You can't really achieve cross-node transactions. In some sense, it's not. I'm literally saying it's not possible because you can't really do a good job, unless and until you're part of the engine itself, to introduce locks, because distributed transactions, to give you atomicity and isolation and the asset properties, you have to be part of the database itself, or database itself has to offer you right hooks to be able to do that. Other than that, you really achieve something that is a hack, in my view. Right? So you'll end up essentially dealing with lots of atomicity and isolation in different scenarios, and you have to work through all the compensatory logic that you would need in case you want sort of, a commit-like behavior that goes across transitions. And of course, elasticity is very difficult. How exactly are you going to essentially, if you were to grow the cluster, then you have a problem, because now you have to figure out how to repartition your data. And again, how do you do it without introducing massive locking, right? It's typically very difficult, let alone all the other operational aspects of from a management standpoint. Okay, so let me jump into SQLFire. There are several products here, by the way. Okay, it's SQLFire. If you look at NoSQL as a class of products now, SQLFire is one. You have VoltDB. You have a product called Clustrix that's out there, NeoDB, and there are several other startups that are all sort of dabbling in the same space, if you may. Different products have different levels of adherence or support in terms of how strong they are in terms of use of memory. SQLFire tends to be, the design is such that we are all about how do we capitalize memory to its fullest extent. So generally, a lot of people think that it's just a main memory database. Albeit you can think about it as a main memory database, as a very strong first-class support for how we'll end up doing essentially persistence and recovery. So from a definition standpoint, you could think about it as it's a main memory-oriented clustered database that's designed to scale not just within my racks or within my network, but it can essentially scale across wide area networks also. So it offers the same NoSQL characteristics that of being able to sort of horizontally scale out, scaling, performance availability, but it also retains support for transactions. And when I say transactions, I mean full asset transactions, right? The ability to do actual distributed transactions across any number of nodes, without really the contention points that one would see with classic distributed transactions, right? The two-phase commit protocol. And then also we think that the number of limitations that you see in comparison to if you may NoSQL stores, where when it comes to real querying capabilities, are very limited, right? Even if you look at even from my standpoint, even if you look at a Mongo or a Cassandra, things like that, even if you see Cassandra, they're emerging with the thing called CQL. It's still very limited in what it can do. So we think that when querying is rather important and scale out and scale is important, this class of products is a much better fit in that sense, right? So there is much more richer support for querying. The other key aspect of just SQLFire is that it's also designed such that it can be an operational layer in front of your database. So you can essentially use it as a sophisticated distributed caching tier. And so it's got things like, hey, if I go and look for something inside my cache, it's not there, there's a miss, it can go and fetch the rows from my backend database, populate it inside, redistribute it, and make it available to the application. Now, the more important things are write through and write behind. So if I change something and I'm in the scope of a transaction, can I do it in such a fashion that I can transactionally or consistently essentially write it to my backend database, make it visible inside my cache, and then make it visible to my application, and being able to deal with failure conditions on things that can. Obviously, when you do write through, you're only as fast as the database on writes, sort of not a very preferred sort of option. And the other option is really write behind, which is to say, hey, let me make my changes to this clustered in-memory thing really fast, efficiently, so I can do lots of writes very, very efficiently. And then SQLFire, in some sense, queues things up, orders it, batches it, and does do batch writes in the back end to the backend database. And batch writing, always with almost all databases, really work much better than individual transactions. So that's the general idea. All right, so here is a sort of a 30,000-foot level view of the architecture, I guess a deployment architecture, I should say. So the core of the system is really a peer-to-peer cluster where you have a set of member nodes that can dynamically join or dynamically leave, and so each node, when it joins in, essentially is able to talk to every other node. So we essentially establish connections. And the ability to join and discover nodes can be based on either TCP or there's an MCAS-based discovery, multicast-based discovery. So you can just broadcast on a multicast channel. Anybody else who's there on the channel can sort of say, hey, I'm in, and people and other members can get inside the system. The access to this is just standard JDBC And today we only have a few JDBC drivers, and then we have ADO.NET or .NET support. Nothing else at this point, but we're evolving to support all sorts of other languages very quickly. One of the nice things is that the whole database engine itself is actually built with Java technology. The core of the technology is all Java. Even though on the client side we have native components, but on the database side itself, it's all a Java database. In fact, we use some of the Apache Derby, IBM's components to actually build this thing. So the beauty of this thing is that you could literally essentially embed your SQLFire servers inside your Spring application. So your Spring container can in turn host the servers itself, and hence you have all the ability to do dependency injection. You can have your Spring beans running inside your database server, and you have tremendous flexibility that way. So like I mentioned, on the disk side, well, when you create tables, I'll talk obviously more about this. We support, on the data modeling side, we support what's called as replicated tables or partition tables. If you create a replicated table and you have a cluster of n nodes, that table essentially by default appears on all nodes. And essentially the replicas are maintained in a synchronous fashion, right? So now you get sort of read scalability by essentially scattering to all this. Or you can, if you go with partitioning, the ability to, we have different policies for how we partition, but the idea is to spread the load across any number of nodes there, right? Yeah. Right. So let me just point, we'll come to that maybe in more detail later on, but the quick answer is that multicast is kind of used only for discovery. All the communication, data communication itself between nodes is handled through TCP, but that's sort of, irrespective of that fact, what happens if there's a network partition? Yes, there's a very sophisticated membership system that's built in that's doing continuous health checks across the cluster. And we use a quorum-based mechanism. That's a quick answer. A quorum-based mechanism such that we kind of, if you look at the CAP model, right? Those of you are familiar with the consistency, availability, and partition tolerance model, which I don't think it's a good idea to continuously reflect on that model, because a lot of the NoSQL paradigm guys do that because it doesn't fully describe. But anyway, even if you look at that simplistic model, we are more towards a C and an A part. In other words, if you ever have a network partition, we simply do not tolerate inconsistent data. We do not want to provide inconsistent data to the application, right? So that to that extent, we are like an SQL database. So if you have a subpartition, we figure out only one partition essentially lands up surviving. That's the answer. We'll talk more about that later on. So you can expand the cluster on demand, add more nodes, remove nodes on the fly. And when you do that, when you remove nodes, if you're set like saying, I needed 2 copies of my data, the system automatically figures out saying, is there memory available so that I can reestablish the copies of data, right? And then the disk architecture is unlike what you'd see with clustered databases. Like for instance, if you look at Oracle 10G or 11G, yeah, sure, you can get n number of Oracle instances running, but at the end of the day, when it comes to the disk layer itself, it's all essentially shared everything, right? So in our world, it's completely shared nothing right to the disk level, including each copy of the data essentially becomes a separate copy on disk itself. And then there's a lot of machinery to say what happens during failure conditions, how do we recover, right? All right, so let's just, let's see how we're doing on time, okay? All right, quickly, so here's what we're going to do. I'm just going to walk through some basic extensions to SQL that we have, and then we'll walk through some demos. So while we're doing this, for the demo purposes, we said, okay, we're going to stick to one schema, and it's a very simplistic sort of an airline availability management system, right? So the schema, a star schema, for those of you, the idea here is for the star schema, you have a few fact tables, right? These are typically your transactional tables, the write-heavy tables. And then you have a bunch of code or dimension tables that are rather fairly static, barely changing. So I'm just depicting sort of these key tables we're dealing with in these demos. So you have flights. Flights have one-to-many relationship to flight availability. And then there is, for every flight, there's a flight. This should actually also be one-to-many, I think, flight history. So we'll assume that in our sort of sample example application, we'll assume there are thousands of flights, right? A flight being, a flight from one source to a destination. And then flight availability is all about how many seats do I have available, how many seats are taken, that sort of thing. So we'll assume that when it comes to flight availability, there are millions of records and it's constantly growing or changing. And then we have a bunch of code tables like airlines and countries, that sort of thing, that's barely changing at all, right? So with that in mind, when you create a table in a normal database, if you're connected to a server, we'll end up creating the table there, right? In SQLFire, and so is the case with all these NoSQL databases or NewSQL stores. You can essentially, there are extensions provided to how you create tables, right? Much like any other database. If you look at Oracle as a database, I mean, you have a bunch of extensions that are just Oracle specific in the DDL. So that's one of the disciplines we try to follow, that, hey, throw some of these new concepts and new rules more at the DBA, more at the guy who's designing the schema, not necessarily at the developer who's coding SQL, right? So a lot of the extensions we did are all DDL, data definition related extensions. And the guy who's essentially writing SQL, if you may, there are some restrictions, but those restrictions are fewer, but the syntax itself is exactly what they're used to, which is SQL 92, some portion of SQL 99, and a few elements of 2003 SQL, right? So here are some extensions, right? So the first is, if you just simply add a replicate clause to that create table, then essentially you'll end up having that table visible on all the nodes just on the fly. So even if you add a fourth node here, that node will automatically manifest that replicated table and grab that initial data from the other nodes and may essentially maintain a consistent copy. So the idea here is pretty simple, right? I mean, when do you use replicated tables? When you have reference data, you'll end up essentially using replicated tables, the tables that seldom change, and they're often referenced in queries. You often use these tables in joins. So airlines, for instance, in our example, perhaps always use, or for that matter, countries, code dimension tables are always used in these queries. So you want to essentially replicate. Partition tables, I'm just giving you one quick example here. There are different partitioning policies we'll talk about in a second. Partition by column, flight ID, the idea is to essentially hash partition on that column, and you essentially spread the load across all the machines available, nodes available. And you typically use partition tables when you're write heavy, right? Essentially, so if you look at replicated tables, it's ideal for read heavy workloads, and for write heavy workloads, a partition table is ideal, right? Or when the data set volume is rather large, so I can essentially spread and capitalize on the memory available across all the machines, and I can uniformly spread the data across all the machines, right? So you can add essentially redundancy clause here. So if you want partitioning and you want to say, hey, I want n copies of the data, you simply say redundancy, whatever number, right? So that's kind of where you achieve some sort of balance, because if you create more copies, given that the copies are all synchronously maintained, you can get tremendous read scalability, right? Hey, I can essentially load balance across any of the copies, and I'm guaranteed that I'm going to get consistent data back, right? So, but if you do that and the data is constantly changing, then you're going to pay the price of replication, right? So by default, I should have said that by default, when you create tables, they're only in memory. So unless and until you put this clause that says persistent, if you say it's persistent, then they become disk resident, and they recover from disk. The only thing that's persistent in SQLFire out of the box is the data dictionary itself, right? But everything else is in memory unless and until you say, hey, I want it persistent. All right, so really quickly, we have different things, partition by primary key, and here it's the simple what you'd see with most of the NoSQL stores, right? Hey, given the key, hash partition it, we essentially use a variant of the consistent hash algorithm to figure out where to map it, and we essentially map it to the node, right? So you get essentially a single hop. This is the best way to scale, right? You get single hop access performance. Or if you partition by, you can partition by n number of columns, and it's a combination of the columns that dictate, what the hash key would look like. You can partition by list, or you can partition by range. I mean, given list and range partitioning, you have a few limitations. In other words, if the number of ranges that you specify is limited to 3, at least in the world of SQLFire, or for that matter, even other databases that support similar notion, you're limited to essentially storing the data in 3 nodes. Sure, you can add more ranges later on, but that sort of typically becomes a limiting factor in terms of scale. We also support partitioning by expression, so you can essentially formulate your own dynamic expression to figure out how to partition things by. All right, with that,
sure.
Go into the demo part.
Oh, this is the pointer. Okay. I want to start by just saying that my demo environment is running on my laptop. I have 3 VMs, which are running all these different components of SQLFire. So my client is not even aware that my different components are running my laptop. So because the connectivity is through TCP/IP. Now this is a typical SQLFire production deployment. So you will have a client-server topology in which one of the important components of the cluster is going to be the SQLFire locator, and the SQLFire locator actually facilitates server discovery and also keeps track of all the servers in the cluster at any given point in time. And in addition, it provides load balancing capabilities to your clients. Now, the servers that you can see here, they actually store all your data. And the data is in the form of replicated tables, partition tables, or collocated tables. Something that is very important to point out is that all these servers are active at the same time. So, you'll see other solutions that will have a master-slave type topology in which you only have one master receiving reads and writes, and then the other slaves only can read the data, or can serve reads to your applications. But SQLFire in that regard is very different. So you can have a number of clients writing and reading at the same time concurrently on these different servers. Now, a very important component of the cluster is also the JMX agent. So it monitors the health of the entire cluster, and it also provides a number of statistics at the system level, application level, and the query level. Now, how you start these different components is very simple. You take the locator start command and then define in which IP address and port number you're going to be accepting connections, and also what are the other locators available in the cluster. For high availability purposes, it's recommended that you have more than one locator. If you want to start a server, you specify again the list of locators and which IP address and port you are accepting client connections. And finally, this is how you start the agent. You connect to the list of locators and then you get visibility to all the cluster. Make sense? Okay. Now, how clients connect to the cluster is via the locator. So the locator, in this case, serves as the logical endpoint for your cluster. So you can have X number of servers behind the locator, but the clients are unaware of that fact. So that's the beauty of that. So whenever the client reaches to the locator will return the least loaded server. Remember I said that the locator provides load balancing capabilities? So because the locator has the list of all the servers and it knows how busy they are, it provides the least loaded server to the client. And from that point on, the client will establish directly communication with the server. And the communication will continue until you finish the session, or if the connection drops, our database driver will automatically fail over to the next available server. So it will query again the locator for the next available server, and then it's going to be a transparent and automatic failover. So your application won't even notice that something like that happened. Okay, so what I'm going to show you now is how the scale-out implementation of the airlines database has been materialized. And also, I'm planning to show you how you can scale dynamically your cluster, and then how you can scale back that cluster without losing any data or without service interruption. Okay, sounds good? Perfect. So let me switch back to Squirrel, which is the SQL client that I'm using. Is that good enough, or do you want me to zoom out? So I have these different schemas, and this is the main schema that I'm going to work with. I have created previously a database with all these different tables, and you can see that they have a little bit of data populated. So if we go to the flights table, we have 500 and something records. If we have to the flight availability tables, we have around 542 records as well. So I'm going to walk you through how we created the schema, just real quick. So in order for me to show you how many members or servers are running in the cluster, let me execute this command. What this is going to do is take a look at the data dictionary tables to gather the list of members currently running on the server. Okay, so right now you see that you have a locator, an agent, and 2 data stores. I had 3 data stores, but I want to show you how you can dynamically add a data store, and then the information will rebalance accordingly. Okay, now real quick, this is the syntax that I use to create an error line. And as you can see, it's standard SQL syntax. The only thing I added to make it replicated was this clause. So with this, I'm ensuring that 100% of the error line table will be on each server of SQLFire. Now, let's take a look at the data dictionary again to see how it's defined. So SQLFire recognizes that this is a replicated table, indeed. Now, because we can have thousands of flights every day, we need to partition the data across the different servers. And we are choosing the flight ID as the partitioning strategy for the flight's data. And then we're setting redundancy to 1. So that means that you are going to have a redundant copy of a flights row on another server. So if one of the server crashes, the secondary copy will be promoted to primary, and you are not going to lose any data. Okay, so now I have a number of flights records, and in my server that ends on 35, I have 294 records, and on the other server I have 248. So the data has been partitioned across servers, and SQLFire has done its best to evenly distribute that data across partitions. Now,
I guess it's not so even right now, because as the number of records increase, you'll see a much more uniform distribution. I mean, and still record count is so low.
Yeah, absolutely. Now, flights availability, it's a child table of flights. So, usually you're going to do a lot of joins that require flights and flight availability. So because the rows are partitioned across servers, you also need that the flight availability rows are co-located with flights. So in order for you to do that, you define the same partitioning strategy as flights, but you also add this clause that is called co-locate with. So you are instructing SQLFire to put the flights availability rows right next to the flights rows that have the same primary key. And again, for redundancy purpose, for HA purposes, you are setting the redundancy to 1. Now, if I see how many rows have been distributed across the different servers for flight availabilities, I have 357 on one server and 161 on the other server. Okay? So what I'm going to do now is just to, keep myself honest, to show you that the rows are actually co-located. So I'm going to find out where which server is actually storing the information for flight ID AA1116, and I'm going to take the IP address of this server and retrieve all the flight ID rows that reside on this particular server. You guys follow me? Cool. Okay, so because it's ordered by the flight ID, I see my first entry there, or my first set of entries is AA1116. Now I'm going to do the opposite. So just, again, to keep myself honest, is I'm going to look for all the flights that are not in that node. So I shouldn't be getting the flight AA1116. And as you can see, there is no flight AA1116 there. So I just proved that the data has been partitioned in one server, and the corresponding flight availability rows are co-located right next to it. Okay? So if I execute this join query, I know that I'm just going after one particular node, which is the node that contains my data. Now, what I want to show you next is how you can dynamically add a node. So before I do that, let me start a node. And in which cases we are going to need to add additional capacity. So let's say that we have an internet promotion, and your business knows that you're going to get more traffic to your website, but you exactly don't know how much traffic. So you kind of do your capacity planning and then make sure that you are going to be covered in that regard. But I mean, sometimes it's impossible to determine how much traffic you're going to get. So what you do is add a number of nodes, and at the end of that, you instruct SQLFire to do rebalance. And the rebalance is just, in my case, taking the data from those two nodes and moving them to the new available node, and then making sure that you are going to get different sections or portions of your data across the servers, so that whenever you get more clients, you have more servers working together to make sure that you are getting the response time that you need. Okay, you had a question, I think.
Did you do something specific in your DDL to say that all your joins should be on the node, and the data that you need for the joins doesn't go across nodes? Do you have to do something specific so that all the related information is here, or how does that happen?
Okay, no, it actually, you don't have to do anything specific. So before you determine the scale out design of your airline, you can identify what are the groups of tables and rows that go hand in hand. And you let SQLFire take care of that. And then whenever you do a join query, GenFire will identify that the subset of data that you are going after is just going to be resolved for one or by one particular node.
Yeah.
But
I think the key here is, given that the metadata of how we are partitioning and what tables constitute parent-child relationships, either through foreign keys or through explicit configuration like he did, is known. What happens behind the scenes is an incoming query that comes in, it's a join query or whatever, right? And you have a set of filters, and if those filters do use the same partition, I mean, essentially they're going after keys that determine partitions, we can immediately prune to the right set of nodes. In fact, I'm going to talk about that next. So.
Okay. So now I want to show you that I have an additional node, and then after that I'm going to show you that I will have. Let me show you this. So I have added this node that ends in 37. Okay. So let's see how the information has been partitioned now that I have a new available server. So now I have, previously we saw only 2 nodes and 200 and something rows across the servers. But now, because we have additional capacity, we were able to do that. Now, what I'm going to do is stop the server. And while I'm doing that, so I'm going to stop the server that I just added. So, in which cases, you're going to experience something like that. Whenever you have a planned or unplanned outage. So, a planned outage might be, you are, you had an increase in demand, but now, the demand subsides. So you need to bring back the cluster to the size it was before. So, an unplanned crash, an unplanned outage is just when your server, goes belly up. So, you should be able to cope with those situations in the same manner. So now, again, let me query the data dictionary tables, and we are going to go back to 2 data stores. Okay? And my last query would be to show you that now the flight information is now residing on 2 nodes, and we haven't lost any data. Okay? So
can I ask a question?
Sure.
So is that based on redundancy?
It is based on redundancy.
Recoalesce and redistribute.
Right.
Right.
Yeah, I think what happens here is, I mean, what we didn't cover, when you essentially grow your cluster, we try to say, hey, can I redistribute? And essentially, what does rebalancing really mean? I mean, are we rebalancing for capacity? Are we rebalancing for CPU load? I mean, or it could be something custom. I mean, what happens right now is it's memory based, right? So you're saying the additional guys came on board and said, here is a gigabyte of extra memory for you. And then we said, hey, in what ways am I already utilizing memory in the existing nodes? And we figure out what's the fair share that he should get. Now, it's quite possible that the fair share he got could actually be literally that portions of data which is really hot. So there's no guarantee now that, all of a sudden actually have load balance for CPU. So that's the other kind of paradigm we're working through. How can I have the right set of policies when you think about rebalancing? But the same applies now, the reverse applies when suddenly nodes disappear, right? If I said, hey, I want 2 redundant copies and he was running with 3 servers, well, shoot, and I lost a node, well, what happens? Right? So we always try to do the reverse, which in other words, we always try to say, hey, we lost some sub-portion of the data, so essentially my redundancy level has been compromised. And now we essentially go through an algorithm to say, how can I reestablish the redundancy level automatically? So we wait for some time. It's a configurable time period because what went down could be such that it could be automated to sort of come back in again. But we try to reestablish the redundancy. Okay, done? Yep. Okay. All right. So what I'm going to do now is just to go a little deeper into this whole notion of co-location and thinking about really scale out for more complex situations. Now, even though this slide kind of goes to some of the design internals, and I'm not going to necessarily go into that. I mean, the point behind this is to say that the norm today, by and large, for online, not the MPP class databases, but for NoSQL or this class of real-time databases, is to say, hey, always go after a key. Go do your lookups or your operations based on keys, and simply put, you just scale, right? Because it's very simple, right? Given a key, and if that's what I'm partitioned on, I can simply hash on that key, figure out a bucket or a node, and I can directly hop to that node and do my operation, right? It's as simple as that. Now, well, if my universe of all my clients can be spread across all the keys, well, it's a simple math, right? I can simply double my capacity, and I should, in theory, double my throughput, assuming the network doesn't become a bottleneck. Well, that all sounds great, but in real life, you can't really do all your access simply using keys, right? You really need joins, you're doing complex queries, things like that. What happens in that situation, right? That's sort of the interesting thing. And that's kind of this illustration here. So if you look at a query that says I'm joining flights and flight availability, I'm doing an equi-join, and I'm filtered by a flight ID AA1116, well, if both these tables are simply hash partitioned, you have this complex thing of saying, well, go hit one table, which is probably the smaller of the two, the flights table, use that filter, fetch all the flight IDs. Now literally you have to take the flight IDs and scatter it to all the other nodes that are essentially maintaining flight availability. And now you're doing this expensive thing of saying, well, guess what? If my flight, the number of records that the flights table returned were pretty large, then all of a sudden it's outrageously expensive because you're moving all that intermediate data set to all these other nodes, doing something in parallel, and especially given classic OLTP applications, that they tend to be highly selective in nature. You don't get thousands of rows back to display on a screen. You typically get a small set of rows back, and you're paging through that row. So it becomes very inefficient. So the point here is that distributed joins are inherently very expensive, and they inhibit scaling, right? I mean, the other thing here is, if you look at traditional databases, they do what is called a snapshot isolation. Given a query that comes to a database, it gives you the view as if the database is not changing at all for the entire duration when the query is executing, right? At the point in time when the query came in, and so if you want to do that, if you want to give that kind of behavior, well, guess what? You have to introduce all sorts of locks across my cluster. Again, it doesn't scale. And that's why you see this pattern that says, well, stick to keys. That gives you linear scaling. So what do we do here? I mean, we don't do, even though the database will evolve to say, well, okay, there can all be sophisticated distributed joins and things like that. Today, the whole idea is to promote, in fact, even in the future, the idea is to promote what we're calling as a partition of a database design, where we are throwing some restriction, some thought process to the designer, right, to say, how should my partitions, how should my tables look like? And what sort of co-location model should I do? Especially if you do want scaling. In other words, if I want to add capacity and I want to get more scale, you have to think, and they basically come down to simply two things, which is, you want to minimize excessive data distribution by keeping the most frequently accessed and joined data co-located on partitions, right? So the idea would be to say, if you look at an order processing system, well, is my most frequent access is based on a customer ID or a set of customers, then you want to say, hey, what are those parent-child relationships across my tables so that I can essentially bring those rows together, right? Likewise, in our case here, we're assuming that flight ID, most of the access patterns are based on flight ID, so can I collocate? The next thing is to collocate transaction working set, right? So to say, what ways does my data change within one logical transaction? Can I keep that working set itself such that it can be collocated? Right? So all of a sudden, in some sense, the traditional database design has all been come up with a logical schema, then do some sort of translation to physical schema. You typically have a very normalized design, and you denormalize over time for efficiency. Here, there is an extra burden if you really want high scale out to say you really need to think about our access patterns too. Right? And that's, even though if you see a large percentage of the MPP class databases, the NetEases of the world, the Teradata's of the world, they all do distributed joins and things like that. But they're focused on, large data sets. They're focused on batch-oriented designs. You want real-time, very low latency access. You have to think a little bit more. I would encourage, folks to read, some of what we did was driven by Pat Helen, who wrote this nice paper called Life Beyond Distributed Transactions, a very worthwhile read where he talks about how do you achieve near infinite scaling in OLTP designs. And you'd see the same thing with Google today, right? Google came with big table, everybody was enamored with big table, with column families, but guess what? That's not what they're using. It's all now, there's numerous applications inside Google, is all based on Megastore, Dremel, and now we see something new coming out, right? So what we're saying is this circle where everybody said, hey, key-based access, everybody started realizing that SQL is in fact very important. I need to be able to do querying across a large form of grids, and what are those principles I can use to do such a thing. In fact, I think App Engine uses some of these concepts too, right? So how do you do this? In our world, you have to think about what we call as entity groups. What are those set of entities across related tables that can share a unique identifier and make sure that that column or columns are in fact present on all these related tables. In our case, it's flight ID is shared between parent and child tables. If you have a runner processing system, it's customer ID. And essentially, OLTP systems naturally, I think, tend towards a mechanism to say, I can in fact think through, given my schema, what are those coarse identifiers, coarse ways by which I can partition. In some sense, it looks like sharding, except that you have many such coarse identifiers, not just one, that allows me to think through about all these partitions. Now, I should share this thing that in SQLFire, it's not that, well, we can only prune, we can do scatter gather queries, but we cannot do complete distributed joins across all, not today, not in this first version that we have out there. And the way you do it, which you pointed out, which is essentially how do you get collocation, is simply by identifying with the collocate class. We can also do this default collocation by simply looking and introspecting foreign keys. Yeah, you had a question, is it?
The complete distributed joins not supported.
Yeah.
So you saw a database, it had all the flight information. Granted, we have all these partitions in memory, but wouldn't we be able to do a distributed join to that actual database, even if it might not perform? We'd still be able to see all the data, correct?
Yes. Well, so today, if you're doing a join, right, like he was showing you a natural equijoin, if the joins rows with the parent and the child and whatever number, if the join rows are all happen to be collocated, it'll all execute. Essentially what we don't do, if you think a little bit deeper, is that we do not today transmit intermediate data sets while doing a join operation across all these member nodes, and which is again inhibits scaling. No, it's not. See, there is no single source which says I can just go to this one guy, much like a cluster database, right? Where when it comes at a disk level, everything is just sort of collocated, right? It's one disk. There is no such thing. Everything is scale out. Everything is shared nothing, right? But that being said, this is sort of something that will come down the pipe here in the next major release. We will have distributed. But the point I'm making is that to an extent possible, you don't want to do distributed joins, because inherently, no matter how we do it, it is going to be expensive, right? That's kind of what, and more you think in those dimensions, more you'll realize a design that essentially just fundamentally just scales and gives you real low latencies. In fact, I think even, those of you familiar with VoltDB doesn't even get to this level, right? It's all about simply running procedures inside a partition and you're done. So here is a quick example that illustrates the point. So if you go select star from flights, I'm just showing three logical, if you may, entity groupings here. So one entity group for, SW200 and a grouping for American Airlines 400 and United 326, where all the records that are related to it are sort of, if you may, collocated and they form one entity group, if you may. So if you go select star from flights where flight ID is 326, I know that I can simply prune to the node that carries this data set. I can safely execute that query just on that node, and I'm done. So the point again is here is that how can I get even my complex queries to simply be pruned to one or a few nodes, right? If I can do that, well, shoot, if I can simply add nodes, and given that all the queries that are running can be spread across all these nodes, I simply get scaling. That's the fundamental idea, right? So if I go, if I even do a join, and the join is based on a filter on a flight ID, now I do know that given this flight ID, I can simply go to this node and I can execute the join query in its entirety, and I'm guaranteed that I'm going to get the right result back. So that's also great to scale. So if I do now a join and my flight ID is actually filtered but combines, uses multiple flight IDs, then again I can just simply scatter this query in parallel to these two nodes, and I can essentially execute it. And finally, if I do a query that is simply going on the origination airport, right? It's not really filtered on the partitioning columns at all, then, well, I just simply scatter that query in parallel across all the nodes, and I gather the results back. So again, if your query rather is a query that is, returning large quantities of data back, or I'm doing an aggregation sort of query, then, the scatter gather does provide a lot of benefits, right? Because now I can sort of, utilize the compute power across all these commodity machines, if you may. All right, so I just sort of end on this thought here. The star schema design is a norm in OLTP. You should think about fact tables, which are fast-changing tables, as natural partitioning candidates. Dimension tables become natural candidates for replication. And that's the idea, right? I mean, especially in doing joins and things like that, can one part of the join essentially be replicated? That's the one way you've got to think about it. So how do you deal with many-to-many relationships? You can't really do all of this thing by simply thinking about foreign key relationships, because quite often you may not have parent-to-child relationships. You might have multiple course entities or entity groups that still need to be joined. So how do you do that? Well, try to figure out saying one end of the many-to-many relationship, can it be turned into a replicated table? If not, at least today in our case, can you run the join logic as a parallel procedure so that now you can essentially execute the entire logic, including the data distribution, through simply a procedure inside the database or inside the cluster database itself. And we'll talk more about how our procedures work. And of course, you can do it in the end in the application itself. So I'm going to give it back to you. All right.
Hey, Jags. Well, I mean, there is a consensus out there that the biggest inhibitor of scalability is a legacy database. So regardless of how elegant or how scalable your application architecture might be, your bottleneck is always going to be a relational database. So fortunately, we have SQLFire. It's coming to the rescue and to overcome a lot of these challenges. And what I'm going to walk through is a number of design patterns that your applications can use, so that you can see the power of SQLFire, how you can go from a distributed cache to a full-fledged OLTP data store and to a global data backbone. So, if you want to boost performance and reduce network latency for your applications, you can certainly use SQLFire as a distributed cache to offload your existing database. So your applications can use standard SQL to read from and write to the distributed cache without any problems. Now, your data is going to be written to the database synchronously. And before the changes make it to the cache, because SQLFire can participate in your container transaction, once the write-through succeeds, your data will become available in the cache. So when you need exactly, a very consistent way to maintain your cache and your database at all times, you can use this particular pattern. So, usually you will have, because SQLFire is not in this case the system of record, you will have some cache misses. So you're going to be looking for data that is not in your cache. So with SQLFire, you can define a row loader for each table. And the row loader is just a callback mechanism. So you define the row loader, and the row loader will automatically go to the database and read the record that is missing using the primary key. Will update the cache and return the row to your application. So it does it synchronously and transparently. So you don't have to call two data sources, if you will. So there is a trade-off with this because you are tightly coupled to the database. Your legacy database will determine the scalability, performance, and high availability attributes of your applications. So if synchronous writes or asynchronous write-through is a problem, it's too costly for you, you can actually write to the database asynchronously. So you can decouple SQLFire from the database. So how it works is SQLFire will keep every data change that happens through the cache will maintain those changes as events in an internal queue. Now this internal queue or SQLFire will actually invoke the cache listener, in this case the DB synchronizer, automatically using two policies. So one of the policies is based on a time interval, and the other policy is based on the number of events that are in the queue. So whichever comes first. Now, for high availability purposes, you can actually persist those queues and maintain redundant copies of those queues on different servers. In addition, you can have listeners running at the same time on different servers, but one of those listeners is going to be the primary one, and the other ones will be secondaries and in standby, in case there is a failure. So even under failure conditions, your database will be synchronized. A very important point here is that this spouses a store and forward pattern. So let's say that for some reason your database is offline, say for maintenance purposes. You will queue all that information in SQLFire. Your applications will continue to run right into SQLFire. And then SQLFire, when the connection gets established, it will synchronize the information with your database right away. So what I want to show you next is I actually have an example of how you can use SQLFire to propagate changes to a MySQL database. Okay? So let me switch back to, was there a question?
So go back to the slide before.
Let me...
What happens if one of the entries in that cache was an exception when the database comes back and you get some primary key issue or something? What happens to these subsequent items that are queued up for update?
Mm-hmm.
Yeah, that's a good question. So the question is, what happens if I'm writing back and my schema or my constraints, I guess, in SQLFire is not the same as the backend. The backend fails. So if you're using what we call as a DB synchronizer, I think that's what he's going to showcase, which is a built-in sort of right behind mechanism. That mechanism depends on or is constrained by the fact that the schema I have in SQLFire is exactly the same schema in the backend. Now, if you, let's say, you still end up changing the schema on the backend, we right now just catch, today, just catch this exceptions, try retries, but at that point in time, is slow things down. At least, well, the queue keeps building up, but the write back would sort of, in some sense, stop and alert gets raised. You're trying to think about alternate mechanisms where that whole thing could get dumped as separate isolated tables, and obviously we'll raise alerts when such a thing happens right away. But the system, your app will continue to just function. It's just that the queues are continuing to build up. That's a difference.
Yeah. Good question. So this is how you define a write behind or a cache listener. So right now I'm using as a listener class an out-of-the-box implementation of the cache listener. It's called DB synchronizer. What I need to provide is the driver, the class name for the driver, and also the URL. And in this case, it's a MySQL database, and I'm using the app schema with the user, with the root user. Now, I want to highlight a couple of clauses here. The first one is conflation. Conflation is the concept in which, let's say that you are updating the same row several times. So you will have like 6 or 7 updates to send to MySQL. You can decide whether to send those 6 updates or just the latest one. So if you enable conflation true, that would mean that you are going to send just the latest change to the MySQL database. And remember that I told you that the synchronization happens based on 2 policies? So this is how you define it. Right now, I have an event queue of 100 elements, and a timeout or a time interval of 1 second. Okay, this is expressed in milliseconds. So whichever comes first, the information will go to MySQL. And then because this is a very simple example, I'm not persisting the queues, and I am defining the number of servers where my DB synchronizer is going to run. Remember I said that you can have a primary and a number of secondary instances? That's how you do it. So let me...
Yeah.
On Blizzard, that happens it's at the transaction level or it's a multiple transaction level?
Yeah, so the question is, does the ordering happen at a transaction level or not? Yeah, so the things that make it into the queue, if you're running transactions, only happen after commit. So it's only committed data in the same order in which it happened on the SQLFire store is how it's maintained in the queue. So think about the queue as a fairly ordered queue of your transactional workload or committed sets.
Okay. Perfect. So now that I define the listener, I'm going to start it. Now, let me show you how you... Oh, okay. So I executed the command twice. Sorry about that. So let me show you how you associate the listener to the table. You just add the async event listener to the table definition, and that's it. And if you at a later time want to change or add more listeners, you can do just an alter table. Okay. Let me see if I'm not sure if I started the listener. Yes, I did. Okay. So now the listener is started, it's ready to go. So if I insert a couple of rows into SQLFire, I should take a look at the MySQL database and see the rows over there. So what I'm going to do first is, again, keeping myself honest, I'm going to show you that the MySQL table that I'm going to populate is empty at this time. So I'm going to the flight availability table, and contents, it's empty. Okay, so now I'm going to execute these two insert statements to flight and flight availability, and let me go back to MySQL. And the row is there. Okay, so what you just saw is that it's a very simple way to start moving your data from one database to another. One of the use cases that that we have, or that I've seen in my past experience, is database consolidation. So let's say that you have a number of databases that you need to keep replicated and in sync in order for your applications to work properly. So what you can do is actually start slowly changing your data source with SQLFire. Your applications can point out to SQLFire. In that way, you add that layer of indirection and decouple your application from those databases. Now, once you accomplish that, you can start, if needed, slowly phasing out those databases that you no longer need, because SQLFire now is doing that job for you. So, whenever we talk about OLTP, we know that legacy databases, relational databases, have not been designed to handle thousands of concurrent users or thousands of transactions per second. So we're pushing the limits on what the relational database can do. So what we need here is to include SQLFire as your primary database so that you can enjoy thousands of transactions per second, sub-millisecond response times, and also linear scalability. So the predictable aspect of SQLFire in terms of performance is very important in an OLTP environment. So as you just saw, that SQLFire can scale dynamically. It's a self-healing system. So if you take a look at the power of SQLFire, you have redundant copies on other nodes. You also have assure nothing persistence. So each node will keep the data on disk individually. And then in addition to that, just like in any other database, you can take online backups. So if you think about it, you no longer need a database behind it, because with all the reliability and with all the guarantees that SQLFire is providing, that is not necessary. So if you remove the the other databases from the equation, your architecture is going to be much simpler. And in terms of cost, the maintenance is going to go down, and the overhead to maintain the database is going to go away as well. Another pattern for applications is to actually embed SQLFire into an existing Java application. And this is only for existing Java applications because, like Jags said, SQLFire is a Java implementation. So, in order for you to embed SQLFire, you just need to include the SQLFire libraries into the application. Now, whenever you connect from the application to SQLFire, it will start what is called a peer server. And that peer server will connect to other peers in the same cluster. Now, unlike other embedded databases like H2, Derby, or HSQL, you can actually have replicated tables, partition tables. You can actually persist your data on your server, and also you can communicate with other members of the cluster and execute distributed queries if needed. And you can just go from a client server mode to an embedded mode just by switching the URL. So the first URL is a client server, it's a thin client to SQLFire, and the second URL is how you run it embedded. Okay, so you wanna?
Oh, okay. We're kind of running late, I suppose. Maybe we'll skip a few things real quickly. So I guess most of you probably are familiar with sort of the map reduce paradigm. The whole idea in stored procedure model is, hey, if I have a data intensive thing I'm doing, I'll get the data intensive logic to be running as close as possible to the data, so you get the most efficient access to data and your throughput generally goes higher. And the map reduce paradigm simply says, now what happens if my data is really scattered, it's really a clustered thing running on a bunch of machines. What you want to be able to do is really spread your logic and parallelize your application logic across those bunch of nodes. So the map reduce, that term is, in my view, kind of pretty abused, right? It was really designed by Google to really do batch operations, right? How can I take millions and millions of page URLs and analyze them offline? Versus this paradigm, even though it shares that same conceptual similarity to say, how can I get my procedure executing in parallel on a bunch of nodes and do a reduction operation? In other words, if each node were to sort of return back a set of rows back, how do I consolidate it back? But really it is designed for real time, right? It is, to me, it's more of an RPC paradigm than the classic map reduce, which I prefer to leave aside. The ability to just say, run this procedure, and maybe the procedure runs for a second, returns my setback. It's about the ability to do real-time procedure execution. So, here is a syntax. There's just standard SQL syntax. If you're running a JavaScript procedure, it kind of looks a little ugly, but you identify your class and your static method. You run that. In our world, what we call as data-aware procedures is it goes to the next level. So you can run a procedure, and when you run a procedure, in this case, let's say it's I'm running a procedure called get overbook flights. If you run that procedure without any of these hints that you see here on the on clause and the where clause, it simply says, hey, go look for and run this procedure. Go look and find out what your cluster looks like. It's got 10 nodes. Run this procedure in parallel on all the 10 nodes. But then a nice thing, well, actually, it just runs it on one node, I should say. Sorry. But then the nice thing here is that to say, now I know that the procedure here is simply dependent on just flight availability. It's not dependent on all these other tables. It just depends on flight availability. And it's all, guess what, not only that, it's only looking for data corresponding to this specific flight A1116, right? So you can essentially, there are these extension clauses. So what we call as this paradigm of data-aware procedures. Can I execute my procedure and hint you? That's the key thing, the hint on the data and dependent on, and behind the scenes we would try to figure out saying, hey, which are those nodes that just carries that data set for that, in this case A1116, and execute it there, right? So, oh, there's a little animation here. So that's one part, right? The ability to just target just the subset. So now you can automatically, you can realize a lot of efficient designs, right? Because quite often what we find with online applications is that you are in fact going after a very specific piece of data, right? If there is, so you can now get this very targeted execution. And in the case of SQLFire, when we execute these procedures, perhaps very controversial, is that we execute your code in process where the data is sitting. Now you have this ability to now literally go and do even scans on the local data set, and you'll get it in nanoseconds, literally, because the rows you're looking for is literally right there. It would give you a reference back. Of course, that does mean that how you write the procedures, you can cause trouble, right? I mean, so that's sort of the trade-off there right now. But we give you that extreme sort of speed by essentially executing these procedures locally and in parallel across all the nodes. The other part is really the ability to do what we call as a result processor, which is a reduced part. How can I specify a custom result processor? By default, when we run it on a bunch of nodes, each guy, let's say, returns a setback. We would just union those results back to you. But if you want to do a reduction, sort of saying, take the results that are coming in, merge it into, as a streaming through, merge it into a single result and return it back, we'd use this thing called as the result processor. And then there are all these options that says, I want to execute it on only a specific, don't want to bombard it across machines. I want to target server groups, things like that, which we haven't really covered. But there are lots of options there to do it very efficiently. I don't know whether, do you want to go through this demo or should we just skip? I want to just quickly walk through
Sure.
Consistency model and then open the floor for questions.
Sure.
Right? That sounds all right. Let's do this. So this is the final pattern, which was the ability to you can daisy chain a number of such clusters. So you can have one SQLFire cluster asynchronously replicating to other clusters. So if you really want wide area access across many sites, so you can use this active replication model across many sites to essentially scale in real time.
Just to recap, at the beginning of this section I said that you can actually have an evolutionary approach to evolve your data architecture. So that's what I was talking about. So you can go from small distributed cache, then you can start writing that information back to your data source for, say, reporting or compliance purposes. Then you can completely eliminate your database, and then you can have a global data backbone, which is using SQLFire. Your application architecture is not going to change, and you can grow. And it's a solution that grows with your business.
Okay, excellent. All right, so given the time, probably we brushing past the consistency semantics. So let me first cover even without transactions, how do we ensure, given that there are n replicas at any given point in time inside a cluster, what happens? I pointed that out before. Anytime you have a replicated copy, either it's a replicated table, which means there are other copies meant on other nodes, or you specified redundancy when you're doing partitioning. In SQLFire, replication within the cluster is always eager and always synchronous, which means if you make a change, insert a row, that row insertion only completes once we essentially have sent the row to the other replicas and have explicitly got an acknowledgement that that row has been processed fully, and that's kind of how it works. But the nice thing here is that the row updates are always atomic and isolated, even without using transactions. So even if you're, let's say, updating n columns within a row, we always ensure that behind the scenes that those n updates on that column is always atomic. In other words, all the concurrent guys looking at that same row are not going to see some partial changes to that row. So you don't really need transactions if you are sticking to this NoSQL wisdom of it's only one row at a time. You always make that's your transaction boundaries. In that case, hey, there are no transactions that are needed at all. We have a FIFO consistency model by default, which basically means all writes done by a single thread are seen by all other processes exactly in that same order, but we do not guarantee global total ordering across all the concurrent threads that are writing, right? So if my thread is doing this logical set of operations saying, well, let me insert my customer record, let me insert my order records, let me insert my line items, all the replicated copies, all the replicas for that data, or wherever the data is scattered, they'll all see it in that exact same order, given one logical thread of execution. But while that logical thread of execution is going on, if other threads are operating on the data, and let's say they're also operating on the same data. In other words, a thread basically said, let me insert a customer, and I want to insert an order, but I'm going to hand it off to another thread saying, why don't you insert that order? Then in that case, you might actually have situations where the orders might show up on some replicas before the customer might show up. But that's where you essentially land up using transactions in case you want to do such things. So the consistency model without transactions with partitioning tables is that here we do give you total ordering at a row level, which basically means for any given point in time, for any given row in a partition table, there's always a single guy who owns that row. And all the replicas essentially get their messages through that single guy. Now, that doesn't mean that this is a master-slave or master-replica kind of model. All the guys in the cluster are, in fact, masters. At the same time, they also act as backups. But any given moment in time, there's one guy who says, I own that row, right? So, and all those guys are essentially.
So, Jags, on that point.
Yeah.
So you mean replica or redundant copy?
I'm using that synonymously. So the thing to be very specific, we use that redundancy term only for partition tables.
Right.
Yeah. So you're right. I mean, I kind of use it interchangeably, but yeah, it means the same thing. I mean, all this sounds great, but really it's all about the complexity is all in sort of what happens when members come online dynamically or enormous number of failure conditions. I mean, I don't really cover how exactly we do view consistency and virtual synchrony. I mean, there are whole sorts of things which we can have. If you guys are interested, we can have a conversation. But what I can say is, the whole transactional machinery and the whole replication machinery operates in conjunction, in cooperation with the whole membership subsystem and the failure detection subsystem. So in case there are any things where I sent your application message, I did not get an acknowledgement back, what exactly should I do? And there is all this collaboration with the membership system so that we guarantee that no matter what, you always see consistent data. The client essentially sees consistent data. If you want pessimistic concurrency, I mean, our concurrency model is really optimistic in nature. If you want pessimistic, we do support select for updates, and obviously it's a relational database, so you have support for referential integrity. Even when the child table and the parent table are actually not really co-located, you still get referential integrity in our model. So if you want to do transactions, we have support for read committed and repeatable read. Those are only two isolation. Well, by default, obviously, it's no transaction. So the fourth isolation level as defined in ANSI, which is a serializable transaction, is something we don't support today. And I mean, for good reasons. Again, the moment you go down that path, you really inhibit scaling. Everything, or every single concurrent transaction has to get serialized to provide absolute total order. It's fairly highly scalable, where there is no centralized coordinator or a lock manager for distributed transactions. And we do that by making two assumptions in our algorithms. We assume that in most cases, the transactions that you'd use with SQLFire in this cluster are small in duration and size, and that write-write conflicts are rather rare in practice. So it's a little bit different than what people might be used to with traditional databases, where if you just use, like, let's say Oracle, there's no conflict detection that happens just by default, right? I mean, you have to either do a select for update or you got to use a higher level of, you can't just do read committed and they'll just essentially line up one behind the other. In the world of SQLFire, even though you can do it by turning a few knobs, by default, what happens is, boom, I mean, if I essentially execute a transaction, the writes simply directly propagate while they're in the transaction to each cohort, essentially each data node that owns that piece of data. And each data node essentially starts, if you may, a sub-transaction. A coordination essentially happens on each data node. But one of the ways we prevent sort of waiting, locking and waiting for too long, is by being proactive to say, well, if I reach to a data node while I'm in a transaction, I'm going to acquire a write lock right away. And if I can't get that write lock, I'm going to back off. Right? And that back off literally means that I'm going to roll back that transaction. I'm going to say, hey, there is a conflict. I don't know what to do. Application, you deal with it, kind of thing. Right? So, and the idea behind that is that by sending these write operations directly to the data nodes, And by acquiring these local locks, we essentially prevent now any sort of global locking. We essentially get these local, just these local locks. Now that allows us to essentially at commit time simply send a single message to the cohorts to say, well, make it so, right? They immediately essentially land up committing. So it's a fail fast and a very proactive, eager locking model that gives us sort of this sub-coordination and allows us to stay away from a central coordinator and locking system. Well, obviously all of this has to work again in conjunction with our whole cluster failure detection mechanism, so it's all wired together. Well, guess what? I mean, I'm just going to skip through this. We touched on this. I mean, the disk, when we work with disks, we work fairly differently than a traditional database. So all I think, rather, what's important here is, if you look at any traditional database, there are two disk artifacts fundamentally, right? One is the transaction logs, the write-ahead logs. As I'm doing my transactions, they're all writing sort of append-only logs. And then, in asynchronously, that log stuff is taken, you're writing back to the real data files, which are nothing but larger, rather complex B trees. And that's where the problem lies, right? The moment you land up with B trees, you land up with massive seeks. And it's amazing if you look at sort of today, even though it's actually 09, I mean, we have had so much advances when it comes to disk capacity and the transfer rate on disks. But when it comes to your latency, essentially the combination of seek time and rotational latency, boy, we only improved from the 80s to date by an order of 2x. Simply because, well, it's a physical movement of a head. Now, of course, flash and stuff like that are great enhancements. But even today, I mean, no matter what, I mean, with RAM and dynamic memory, the speeds are an order of magnitude better than flash. But the thing that we do is we essentially try to do a lot of things in a design so that we never seek, right? In SQLFire, for that matter, several other products in the class, there is no such thing as a B tree sort of, where you manage data. Your data is nothing but a bunch of these log files. Then these log files are maintained on multiple nodes, multiple copies exist on multiple nodes, but as you're doing your transactions, everything is just simply being appended to these files. And in fact, we do this thing where by default, when you write to these log files, they don't even flush all the way to the disk. And we mitigate any risk of failures by making sure that your primary and your copies on these other nodes, they're all doing the exact same thing. In case things fail, we can sort of become a little bit more pessimistic in terms of writes. And that gives us tremendous write scalability. We can write at pretty high speeds. And I'm just going to end this with sort of, here's a quick view on, this is a little bit of a sales pitch here, right? I mean, you scale from 2 to 10 servers. And here is a simple thing that says, what happens to queries, and I'm increasing the number of clients from 200 to 1200, and you get sort of queries per second going from 200K per second to about 1 million a second. And then this essentially shows, what happens to the CPU. I mean, essentially this is depicting that, hey, the CPU load actually on the servers is still relatively low. In this test, it was a client that was actually bottlenecking, right? In other words, I'm saying that even with 10 servers, you could get even higher scaling than what is depicted in this picture. And what happens to the latencies, right? I mean, so, relatively low and relatively sort of stable. That's the idea, even with concurrent load. Okay? I guess that's it. I mean, which gives us about 5 minutes for Q&A. I don't know if you have anything else you want to add. But.
In your original demo, when you added the third node, did the co-located data get redistributed as well?
Right, yeah. When you move the rows, and it's co-located information as well to the other servers.
Would that be an online operation if you're, if you had billions of records?
Mm-hmm.
Add nodes as well.
Yeah. So, but the point here is, when you add a capacity, right? I mean, the assumption would be that you're adding some fraction. You're just providing some fraction of the resources that I already have, right? So what we will end up doing is to say, well, you gave me 50 additional gigabytes, and I'm already using 200 gigabytes. So all I have to really figure out is, well, what kind of, maybe it's just 25 gigabytes of data that I have to transfer to this new guy. So that's kind of what we go through, right? I mean, we typically don't assume that you're going to just double the entire thing right away.
And it's a background process, and we don't want to compromise, the SQLFire cluster serving your clients. So we do it, in the background very efficiently, so we don't bottleneck the network as well.
Yep.
in the real world, given that the nodes are persistent and replicated, and you got these redundant copies, about what number of nodes would you estimate that it would start to bog down? Like, I'm thinking hundreds of nodes, if GemFire is under the covers.
Yeah, it's a good question. Yeah, I mean, in fact, it could be even at a lower count. Here's what I would say, right? If your access patterns are such that they can simply be pruned to a small one node or a few nodes most of the time, and all the client load can be spread across their entire data set, it simply comes down to saying the network typically becomes a bottleneck. Right? That's what we see. I mean, we see that, when you have a large number of nodes, what we find typically is that you don't have those number of nodes in a single rack. So you typically have a switch between these racks going, and the switches essentially start throttling to some extent the bandwidth between these racks. And we see those kinds of challenges emerging, that the network becomes much more important, even if you had, but the key here is the access patterns, right? Can the access patterns be such that they can really take advantage of pruning to the nodes? Yeah.
What's your recommended size for JVM? How much data we put?
A lot of the tests we do go to about 40, 50 gigabyte, maybe 70. That's more about the labs and the machines we have in-house. But increasingly we see that we are seeing JVMs with even higher capacities that we're using, right? And the rule of thumb here is the larger the stuff you're going to throw in a JVM, the more room you need to leave for the garbage collector to do its thing, right? So that's kind of the rule of thumb. Any other questions? Okay, thanks a lot, guys.
Thanks.